Good afternoon, everybody. Welcome to our webinar on real-time accurate 3D scanning in inaccessible underground cavities with the new CAL-S HD system. Just some housekeeping rules, please. If you can all keep your cameras switched off and your microphones on mute. And then if you have any questions during the course of the webinar, please feel free to add it in the chat. And we can either circle back to it at the end, or one of the team members will cover that in the chat itself. The meeting is recorded as well, and the recording will be sent out to everybody that has registered afterwards. So just looking at the agenda, so we'll do the introduction of the speakers, and then we'll introduce the new CAL-S HD. We'll go through some CAL-S user cases. We look at some of the other Carlson laser measurement devices. Anthony will provide a CAL-S HD practical demonstration, and then at the end we'll have some Q&A as well. So the presenters of today, I'm the host, Cobus Botha. I'm the Technical Sales Support Manager for Optron. With me, I've got Michael Harrison. He's one of our Technical Sales Support Specialists. And then Anthony Comber from Carlson LMD, and he's the Sales and Technical Support Specialist. So next up, Michael, I'm going to hand over to you.
Perfect.
And you can do the introduction to the CAL-S. Thank you.
Thank you, Cobus. So everybody, I'm going to share my screen now.
Great, we can see it. Thanks.
You can see the beginning of my PowerPoint.
Yes.
All right. So, hi everybody. Thank you very much for joining us this afternoon. Appreciate it. So, just a short bio about myself. I'm Michael Harrison. Graduated with a BSc in land surveying from the University of KwaZulu-Natal in 2017. Was registered with the South African Geomatics Council as a professional land surveyor in 2021. I'm also a South African Civil Aviation Authority registered drone pilot, and I joined Optron in 2022 in the tech support team. And in the beginning of 2023, I was moved over to the technical sales support, and now I run the technical sales support division for reality capture. So basically the general laser scanning. Today we're going to be speaking about the Carlson CAL-S HD. A lot of you might know, or those of you who will know about the CAL-S know that it's a borehole deployed scanner. The majority of people that have used the CAL-S will not have used the HD. It's very new. So on the first slide, I'm going to go through the history of the CAL-S. The CAL-S was developed in 1996. It was obviously a lot bigger back then, being 120 millimeters in diameter, and it took 4 to 5 hours to complete a full scan. We'll go through the scanning process and everything like that throughout the webinar. Yeah, in 2005, the Mark II was introduced. It was obviously slimmed down with a little bit more gyros and pitch and roll sensors. In 2018, the CAL-S gyro was released. This is the CAL-S that most people will be familiar with. This is the CAL-S that the majority of us at Optron here are familiar with. Yeah, so this is what we have done the majority of our CAL-S scanning with, and the use cases that we have been done with the CAL-S gyro. And then in 2023, the CAL-S HD was released. So what is the CAL-S HD? So CAL stands for Cavity Auto Scanning Laser System, and the HD stands for High Definition. So basically the differences here between the CAL-S gyro and the CAL-S HD, you're basically looking at just a color HD camera on the nose of the CAL-S, whereas the standard gyro CAL-S has a black and white camera with red LEDs. The new CAL-S HD has bright white LEDs and a much more high definition color camera. The CAL's diameter is brought down to about 50 millimeters, so it can be deployed through reasonably small drill holes or through the center of certain drill bits. It's primarily used to create 3D snapshots, 360-degree scans of the inside of very inaccessible voids. So generally, when we talk about inaccessible voids, we talk about voids in underground mining, stoping environments where you can send in other types of scanners because there is reasonable room, or you can send in autonomous drones or whatever it may be. However, in the case of the CALs, it is used primarily where there's very, very limited access, i.e. limits access via a borehole primarily. It's pretty much the only scanner on the market that is the size it is and can scan the way it scans. So we're going to talk about the CALS HD. So here is a close-up photo of the front of the HD. It works off a time of flight laser. So obviously you get the time of flight and the phase shift laser. So this is a time of flight laser. It's got a range of about 150 meters, 3 to 5 centimeter accuracy. So not the most accurate laser, but it can get into places that no other laser can. It has both vertical and horizontal movements. This will be displayed by Ant at the end of the webinar. He'll show us how the CALS moves, and you'll get a feel for how it actually works. So if you look at our little picture, you can see in the front of the CALS, there's the color camera with the white LEDs. This is used primarily for the deployment of the CALS, and also in certain instances, if the void is small enough, you'll be able to create color imagery and color videos of the inside of your void as well. And on the side, this is what makes the CALS very special. The laser is situated on the side of the device, and that is your transmit receive optics. And the reason it is situated on the side, not the front, like you would expect, is because of the way the CALS swivels, and you'll see this when Ant does his demonstration. It allows a full 360 view around where the CALS is, and not simply a 270 or 285 view, where generally, like most scanners, the piece behind the scanner is not captured. So we're going to talk about why deploy a CALS, and then we're going to speak through a standard borehole CALS deployment. So you can see here in this image, you can see there's a void. We have a void underground, and this is the case in many mines, whether it's a natural void caused by that could cause a sinkhole in the future, or if it's old underground workings. The reason to deploy a CALS would be to accurately map this void. So in other ways to capture this data, obviously we have ground penetrating radar or gravity surveys. Both of these methods will give us an idea that a void exists and an idea about where it sits from relative to the surface, but we will have very little data with regard to actual size, volumetrics, and whether the void is changing or not. And this is quite important data. So we could know voids exist, but to know exactly how big they are, where exactly they sit in relation to each other, is quite important, as all the guys on the mines will know. When it comes to planning, blasting, and drilling and mining operations, understanding where voids may sit or where old underground workings may intersect can result. Not knowing where these things would sit will result in catastrophic failure or sinkholes. So it is very important to map these voids as accurately as possible. So now we're going to speak through. I'll talk you through a standard CALS deployment via a borehole. So in the slide previously, I showed you we had a void. We know a void exists. We sort of have an idea of where the void is. And now I'm going to talk through how to accurately scan this void using the CALS. So the first port of call, once you have a reasonable idea of where the void is, in the case of old underground workings, there may or may not be old survey plans or models of the void. So there's varying degrees of knowledge about where the void is, the size of the void, has it changed? In this example, we have a reasonable idea of where the void is, so we are capable of drilling into the void. That's always important. Once you have set up your drill hole and you have entered the void, you've drilled a hole into the void, you're sure you've reached the void with the drill bit. You then, standard practice would be to collar the hole for the first few meters at least. It is then very important to accurately survey the collar position of the hole. In an open pit scenario or an outside scenario, a survey grade GPS is sufficient. However, in underground scenarios, a total station will need to be used to fix the center of the collar position. This coordinated position forms the base or the starting point for your survey with the CALs. You will then have the CALs sitting on a calibration jig. As you can see there, you have to give it a starting heading. The starting heading can be given in a few different ways. You can align it along a known heading. You can fix the front and back of the CALs with a survey grade GPS in the case of open pit surveys, and then calculate a heading, or give it starting and beginning and back and front points, which will calculate a heading itself. You can see there's two small targets that can be added to the jig. These can be fixed with a total station underground to calculate a heading for our CALs. Once you have once you have surveyed the collar position and you know the starting heading of the CALs, you're then able to begin your deployment. So you can almost consider it, or almost visualize this as an open loop, as an open traverse. So you start on a known point, which is the collar position, and then you feed the CALs down the borehole, taking regular measurements so that you can track the deviation of the hole, or the position of the CALs as it travels down the hole. There's quite a lot of technical techniques into getting this correct, so we won't go too deep into the maths behind how it works. But basically, there's an IMU and pitch and roll sensors that the CALS is using to figure out how it is moved from its original heading, and given its original starting position, it's calculating where it is every time. For example, every 2 meters, you'll take a reading of where the CALS is. This is the view you will have on the CALS screen. So as you are deploying your CALs down the hole, you will have a control tablet or computer out with you in the field. That'll be linked directly to a live stream from the camera from the CALs. That's the camera in the front of the CALs. You also have a picture of how the CALs is deploying, so you will see how the CALs is moving down the borehole, as well as a live feed of the camera. This will allow you to, as you can see here, this will allow you to see any blockages in the hole that may be coming, because as a lot of us know that have dealt with drill holes or boreholes, quite often there are cave-ins of rocks. This happened to me very recently. This is the one use case that I would love to have shared with this webinar, but unfortunately the data is still in use, so I was not able to share it. We had a void that was so big that it had to have 3 drill holes drilled into the top of it, and the third drill hole continued to cave in with rock, so it had to be rebored 3 times. And using the live video feed from the CALs, I was able to determine the blockage before the CALs rammed into the blockage. This is quite an expensive piece of kit, so you don't really want to be using it as a borehole cleaning device. So when you do see a blockage, like you can see in the middle picture, it is best practice to stop deploying the CALs rather than allow it to be rammed into the blockage. Here you can see a video of the CALs entering a void. So at this point, you have entered your void, and this is where you're gonna set your scanning position. So as you can see in this picture, you have completed your open-ended traverse, so to speak. The front of the CALs is now poking out into the void. You have secured the CALs in position, and you've taken your final reading. And as you can see by the little yellow circle with the cross, the position of your collar has now been transferred via IMU measurements and measurements on the tablet to the final position of the CALs. The CALs is now in a position where scanning can be done. So the CALs is in its final position. You have sorry, I'm forgetting the word. You have secured the CALS cable in place so that the CALS doesn't move. Once you've taken the final measurement, any movement in the scanner from there will introduce errors in your scan. You are then able to start your scan. You have a number of options when it comes to density of your scan. You can move the head of the scanner by 1 degree, by 2 degrees, and by 3 degrees, about 5 degrees each time it does a rotation and a data collection scan. This will increase or decrease the gaps in your data. The most dense scan is a 1 second or 1 degree scan, and this takes about 22 minutes for a full 360-degree snapshot of what is around the CALs. Now you can see in this picture, this was pointed out to me yesterday, it looks like the CALs is unable to scan this top piece, but this is simply a snapshot of what the CALs would be looking like, what the scan would look like when it is nearly complete with the scan. However, it still will scan up behind itself. You can see in the Carlson scan software, you can select to build the mesh of the scan in real time. So there's still the top corner of the data picture that will need to be built, but just to put your minds at ease there. So yeah, here's a video of a scan position from a scan taken from one position from the CALs. So as you may be thinking, so what happens if the void is bigger than we expected? And now, for example, you've made a drill hole into the void, you've collected data, and you can see, oh, there's serious blind spots or holes in the data. So in that scenario, you've captured data, you understand that the void is bigger than you thought it was, and you can then move forward to drilling a few extra holes into the void in order to capture the majority of the void. Whether you want to use this data for volumetrics, for mine planning, to see, even if it's a void that you know is there, and you have models of in the past, it's a good way of re-scanning the void, allowing you to see if this void is in fact self-mining itself or not. In many cases, especially in the case of where there's old underground workings and then an open cast coming down towards these old underground workings, all the drilling and blasting from the open cast can cause that void from the vibrations to start self-mining, and you'll find that in your records the void is a certain size. However, it might have grown considerably over the years without you knowing, due to the vibration from the drill and blast of the open pit. So though we've touched on a few of these things already, but yeah, so we'll talk about the dangers of voids in an open pit, and this also translates to the dangers of voids in underground workings, where old underground workings are intersecting new underground workings. So yeah, in a lot of places around the world, mines have been going on for, as you would know, most of the guys that are on the mines have been going on for many years. The mines have changed ownership. They have moved from underground to open pits. There might be natural voids. The area, the rock that is around that area may be prone to natural voids or sinkholes, and yeah, this can cause a lot of damage to property and lives. And as we all know, safety is the #1 priority on mines these days, or has been for a while. And one system, one CAL system, can be worth a human being's life, which is incomparable. I heard a story recently where where CALs was being deployed, and now keep in mind, if you are inexperienced at the CALs deployment and your hole comes at a non-vertical angle, so it comes at a slightly shallower angle and pokes into your void. If you're inexperienced with the CALs and manage to push the CALs the whole way through the hole and the cable flops into the hole, there's a high possibility you're not going to get that CALs back, especially if the borehole is the only access into the void. So in the story I was being told, there was a man who was willing to push the limits and keep pushing their CALs further and further into the void, just to try capture as much data as possible. And the one guy even said, it's honestly, this data alone, this one data set alone is worth more than the value of this CAL. So I'm just gonna keep pushing this thing to capture as much data as possible. And yeah, that just goes to show that in some instances, if there is no other way to get an idea of what's going on in there, and it's holding up mining, and it's holding up planning, and it could potentially cause a fatality and hold up the whole mine, yeah, the data can be very valuable. So now we're gonna move on to a nice short use case. I have a use case from the beginning of this year, when I scanned a void via 3 drill holes in Namibia. However, at this stage the data is still being used, and yeah, it was not. Uh, I couldn't get it freed up for use here. However, this use case was done by our host, my co-host, Mr. Kobus Buerta. He did this a few years ago, and yeah, we can talk about it. So, user case verification of old stopes. So in this case, we're going to be talking about the Gamsberg zinc mine in the Northern Cape. Gamsberg is located near the Black Mountain mine. It was an old underground Anglo-American mine, which was subsequently sold to Vedanta, who the company that now owns Gamsberg and Black Mountain, who decided to start open pit mining the same ore body. And obviously they started getting closer and closer to the voids. I mean, they knew there were voids down there. They knew there were old underground workings, but they needed to verify how close they were getting. So Mr. Kobus Buerta here went over there, they did both a drone survey of the open pit and also a survey with the CALs of the numerous voids that were located underneath the open cast workings. So here's a picture of our setup. This is your standard CALS calibration jig, lying near the entrance to the hole. There's a deployment wheel that we here at Optron developed. It's got cleats that allow you to lock the CALs in place during the scanning process. I use the exact same deployment wheel in Namibia, and it was a absolute lifesaver to have something to lock the CALs in place, because when it's down 30-40 meters, it gets a little bit heavy, and you don't want to hold it in position yourself while it scans for 22 minutes. But yeah, so as you can see, there was no other way to get to these underground voids via the surface, and these drill holes were the only way to verify the location of these underground workings. So here's a nice depiction of the underground workings overlaid with a very pretty drone survey of the open cast workings. As you can see, they were getting pretty close to these underground workings, and it was a very good idea for them to get us in to do a proof of concept. You can see the white lines going down from surface to the voids. Those are the path tracked by the CALs. I was chatting to somebody recently, and I was explaining to them how the CALs worked, and they asked me, but no, isn't that the bore track, the Carlson bore track, the bore track that is also developed by Carlson? And I had to say no, it's not. Although the bore track does do something similar, it does also use similar technology to track the track of a borehole. However, CALS uses the same technology, but to calculate its final position in a void, to then be able to scan that void on the same system as the collar position that is coordinated, whether that is LO, your local mine system, UTM, WG, Hotspurs hook, doesn't matter what system it is, as long as the collar position of the hole and the heading of the CALs in the beginning of the survey are on the same system, then you'll be able to deploy the CALs, and taking care to take regular measurements and make sure the data on the controller or on the controlling tablet or controlling computer is the same as what's being done in real life, feeding the CALs down the hole. You'll ensure accurate georeference scans of your voids, whether it's one drill hole, two drill holes, three drill holes, as long as you follow the correct procedure and scan correctly, you'll have no issues with scans not fitting together, and you'll have a perfectly registered and georeferenced, like you can see here, example of underground workings overlaid with the reality of what's going on above surface. So yeah, that's really the CALs in a nutshell. It's a very versatile tool. Very useful when it comes to scanning underground workings through boreholes. Obviously, there are a number of other scanners. We know Carlson developed the void scanner. There's a number of autonomous solutions that go into inaccessible per se voids. However, the void scanner is still sent into open stopes where there is access via access that would be used by haulage vehicles to remove the ore. The CALS is the only scanner produced by Carlson that can scan voids where the only access is via a borehole. And that is me. Thank you very much, guys. I really appreciate you listening to my very basic explanation of how a CALS works and a basic deployment of the CALS. Remember, guys, if you have any questions, you're more than welcome to put them in the chat.
Thanks, Mike.
Pleasure. Thank you for the
really informative. Next up, Anthony, I'm going to hand over to you, the practical demonstration. Thank you.
Okay, can you see me okay? Yeah.
Yes, we can. Mike, maybe you can just switch off your camera, and Philip, Checo, if you can also just switch off your camera, please.
Guys, I'd just like to say there are some questions starting to pop up in the chat, so I'll wait for the end. We'll have a few minutes at the end to answer your questions.
Okay, yeah, thanks, Mike. So I'm Anthony. I'm in our Carlson's office in the UK, just near York, where we design and manufacture all these products. So I've got here one of the CALS probes that Mike's been talking about. So this has been quite well used. Obviously, as soon as it's used, it gets very scuffed up and looks the part. But so the actual probe is about a metre long, and there's actually a 1 metre extension piece that fits on the end. So I haven't fitted it together because it gets quite unwieldy in the office. But when it's all fitted together, this probe is 2 metres long. And the fact that it's 2 metres allows you to, when you enter a void, you can push the head right out into the void while still allowing part of the extension piece to be secured in the hole. The advantage of pushing the head as far as you can into the void means that it can see maybe further around any obstructions, any rocks sticking out. So obviously the CAL-S takes a bit of a battering as it's going down the hole. So it is built to be rugged and to take quite a lot of use, but at the same time, we do need to take reasonable care with it. You can see on the nose of the CAL-S here, this is the HD camera, and around it is a ring of LEDs. So actually one of the videos that Mike showed you in his presentation of the probe going down the hole, that was taken with our old camera, which is black and white and a bit more grainy and not very powerful light. Whereas these lights, when they're turned on, will allow you to see maybe up to 25 meters in the void. So rather than just being blackness when you enter the void, you can actually see, around you. So the camera is pointing directly along the probe, and on the side of the probe here you can see the laser lenses. So the laser is shooting perpendicular out from the probe and the camera is shooting along the nose. So the camera you want to be able to see as you're going down the hole, any obstructions or whether the water's filled the hole, and most importantly, you want to see when you exit the void. So that's why the camera's pointing that way. But the laser's pointing out, and as Mike said, it's hinged. The CAL-S is hinged this way, so we can see back where we've come from, and we can see directly away from the probe. And then the probe is pivoted horizontally as well, so it can see in 360 degrees when you're doing the scan. So there's no blind spots. And inside the probe, we've got the motors to drive the pivots, and we've also got an IMU, an inertial measurement unit, which will measure the angle of the probe and the heading of the probe as it's going down the hole. So, as Mike said, as long as you know the starting point on the surface, you can then effectively traverse down to your scanning position, and you'll know where you are in relation to your position on the surface. Okay, so this CAL-S is connected by a thick weight-bearing cable to a surface unit, which is with you on the surface. And this is just a junction box for power and data and the camera image and so on. So when you're ready to go, you hook the CAL-S up to the software. So I'm gonna, I'll start the software now, if I can just share my screen. So hopefully you can see now, this is the Carlson scan software. So
yeah, we can see it. Thank you.
Okay, so once you're ready to go, this will be running on a tablet, a ruggedized Windows tablet that you'll have on the surface. It's designed for big buttons, so you can touch it easily with muddy hands or gloves or whatever. There is as you see here, there's a desktop button. So if you're using it back in the office on a bigger screen with a mouse, you can go into desktop mode. But I'm in the kind of field mode. So if I start a project, so let's call it. So you can go straight in to connect to the CAL-S. Also, we can import collars. So if you have a bunch of collars that you're going to be deploying down, and you already know the coordinates, you can import some collars. So let's see if I've got any collar coordinates here. So this is just a CSV text file with some collars, the names and the XYZ coordinates of the collars. So if I import those into my project, these are all the starting points for my deployments, the collar, surface collars. So if I create this project now, we automatically connect to the cavity scanner. And so in this corner, you can see the video. You'll see my very, very messy office. Not much to see, unfortunately, but you can see kind of what's going on there. And on the right, these are all the collar positions that I've imported into the project. So if I go to my project, each of these is one of the collars, and if I click on it, I can see these are the coordinates that have been surveyed in. If you don't know the coordinates ahead of time, you can survey them afterwards and just enter the details after you finish. That's okay, back in the office. Okay, so I mentioned there's a IMU in the probe. So the IMU's got a gyro in it. The gyro isn't a north-seeking gyro. You have to initialize it in a certain direction. So what we do is supply a jig. If you can see this picture here, there's a jig sat on the floor, and the probe, you see the probe here with the extension piece fitted. You'll lay this out on the surface by the collar, and you'll either position this along a line of known orientation, or you can survey in the orientation as it is laid out there. So let's say you survey it and it's 70 degrees. That 70 degrees will be your starting orientation for the scan, for the deployment. So once you pick up the probe and move it around, the gyro will be tracking the change in heading relative to this known starting heading. So when you're ready and the probe is in the jig, we hit a line, and then we give it a whatever the starting heading is, and this will now initialize the probe, initialize the direction of the probe, initialize the gyro effectively. So let's say we start from hole for the collar 10, so you can see the CAL-S here, and if I move the CAL-S, you can see it's in real time. It's reflecting the actual inclination of the actual probe on the screen here. Now, particularly if you're working underground, it's good you can bring in background information, so you've got some kind of context. Again, you don't have to do this, but for example, you can import. Let's import some models here. Okay, yeah. So because we can see in real time as we're deploying and scanning, it's quite nice to have a background that you can work with, and you can see immediately whether you've got any gross errors or any problems, and whether your scanning is exactly where you expected it to be. So you can bring in all sorts of survey data. If you've got survey points in your tunnel, you can bring all those in. So everything is related to what you're doing in real time. Okay, I'll just turn those off for the moment, but you can see that it can be very useful, particularly, as I say, if you're underground. Okay, so we're working from hole 10. So we're aligned. We've got our basic alignment. So now you take the probe off the jig. We're going to be deploying every 2 meters down the hole. So essentially, at this point, you now deploy the probe 2 meters into the hole, and we take our first reading. So at this point, the screen just switches, because the main thing you're going to be watching as you deploy is the camera, because you want to be absolutely sure you know exactly when you hit the void and exactly when you are coming close to any obstructions, that kind of thing. But you can also see the graphic on the left here. So, oh, sorry, on the right. So every time I take a reading, you'll see the probe advances by 2 meters. And if I change the inclination of the probe, I mean, this is obviously very unrealistic changes in direction, but you'll obviously in the real life it will be subtle, but you'll be able to see basically you're building up a model of the hole all the way through into the void. And the camera image, obviously, if you're going down a hole, what you'll be seeing is like this kind of thing, like the inside of the hole. So you'll be monitoring this as the guys are deploying it down the hole, and so you'll keep deploying. And then when you're in the void, you then secure the CALs in place, and now you're ready to scan. You can use the camera to have a look around if you want to investigate. So we've got a little joystick here that you can use, and if you want to have a look around, you can do that, and you can record snapshot images, and you can record video if you want to look all the way around, if you kind of something you're interested in seeing it. I mean, sometimes all you'll be interesting is a volume, in which case the scan is all you want, but sometimes the actual, the condition of the void is important. So back in the project, everything that we record is recorded in this project tree here. So you can see we're in hole 10. We've taken a screen capture, and we've got a deployment going on here. So we've only taken a few readings, but you can see each reading is recorded, and you can go back and analyze where you've been and just export the deployment if you want. And then when you're ready to scan, you go into the scan tab here, and you can determine how dense a scan you're going to run. So you might want a very, very quick scan just to get a vague idea of how big the void is, or more likely you'll probably do quite a detailed scan. So this is a 1 degree scan, it'll take about 20 minutes. You can do much more detailed scans if you've got a lot of time on your hands. I'll do a very, very quick scan, so this is only 4 minutes. So if I press scan, we'll now start scanning. So bear in mind, this might be dangling in the hole and spinning a little bit as it's scanning, but the gyro can compensate for that as it's going. So you can see, if I zoom in on the head, you can see how it's shooting away from itself to start with. And if I just swap to, if I show, sorry, you can see me now. Sorry, you can see the actual probe, hopefully. So you see the 3D image in the software mimics what's going on here. So the laser is pointing directly away to start with. It completes a horizontal rotation, and then it moves vertically. And so the amount it moves vertically defines how detailed this scan will be. So the smaller the vertical increment after each horizontal scan, the longer it'll take and the denser your data will be. Okay, so I'll just stop that a second. I moved the probe, so it's kind of nonsense. But this is the this is how we start scanning. So I just deploy a little bit further so we're clear of that. Okay, so if I just start again. There. Okay, so we start scanning. We're looking directly away from itself. If we can record the camera while we're doing this, but remember the camera is pointing out the line of the head there. So the camera's looking at something different from the scan. So in my project, you can see I've got 2 scans. So I'll turn the first scan off. So we're just looking at the first scan. And as we're scanning, you can actually build up a mesh in real time. So you've got a model building up. So that's a kind of wireframe model. Okay, so there we go. That's And as I say, if you had your models on, you can kind of see that you're scanning where you're scanning in relation to maybe what your design plans were for underground, or what your last surveyed data is. So you can see maybe the void's collapsed or something. So you can actually see as you're scanning and maybe start thinking about what this means, what the implications are of where this void is sitting and how big it is. So you can also take measurements as you're going. So just taking, obviously this is in my room, so it's only 4 meters across. So generally, yeah, the time for a scan is taken up by mainly getting to the site, deploying all the equipment, getting it set up, deploying it down the hole. So by the time you've done all that, you would usually may as well just run a full 20-minute scan. Kind of makes sense. The smaller the void, then the quicker the scan needs to be. For this, my room, something that's only this size of my room, just a few minutes is perfectly adequate. If all you're looking for is a volume, you can combine that maybe with an inspection with the camera. But if I spent 20 minutes scanning, it wouldn't affect the actual volume I'm getting from a void this size. It's becomes fairly immaterial. And so anything you collect in here can be exported. So we can export the point cloud if we want to. We can export the surface model, and we can export the deployment trail there if you want to as well. As Mike pointed out, sometimes you go into a void and you can't see everything. So maybe there's something blocking your view of the void over this side. In that case, you can drill another hole into the corner here. And as long as you start from a known surveyed collar coordinate, and as long as you initialize the gyro in a heading that's on the same coordinate system, then you can deploy into another part of the void and everything will mesh together fine. Okay, so this is a very quick scan. I'll just leave it to get to the end of that. Now I've moved, my office is very, very messy. There's lots of things hanging up, and I moved the CALs a bit so you can see it's all messy, and the laser's going out the window here, so there's a bit of spray and reflecting off the light fittings here. But if you're just shooting to rock, it's just a solid, a more solid and obvious void that you're getting. If I go back to the, so it tells you here we've 39 sweeps, we've done 37, it's 90% finished. And okay, it's just finishing up now. Okay, so that scan's completed. So that was a 5-degree scan, 58,000 points. And if I go into the scan tab here, I can just, if there's any little holes in there, there might be a little hole where we've entered. I can fill holes, and if I fill the holes, it then gives me a volume for the void there straight away. So yeah, that's introduction to the CALs. I can perhaps just show you a maybe one that we've done. So if I just open this one up here. It's not gonna. Okay, well, at least that happened at the end. I just opened the. Okay, let's just open up a project here. Okay, so this is where we did the actual scan with these tunnel and stope models, and you can see actually we were planning on going all the way down, deploying all the way down into these old stopes, but we encountered a void halfway down the deployment, which was completely unexpected. So this scan here is made up of, we entered this void in 3 different places and they all match together. And from that you can see they were able to get a volume and to inspect with the camera, see what was going on and why this void had opened up. This is something they didn't know about at all until we deployed the CALs into it, and they had no other way of reaching the void as well. So they were backfilling, so it helped them to judge how much paste they were going to require and what other holes they needed to drill. And this was part of a big program of reassessing a lot of very old stopes that they hadn't investigated for a long time. So yeah, the CALs was pretty much the only tool that they could use for that. Yeah, so I think that's about it. And that's introduction to the CALs hardware.
Thanks, Anthony.
Okay.
That was really cool. So thanks, guys. Next up, we're getting to the questions and general discussions portion. So Michael, I see there was some questions in the chat. First up, so you partially answered it. Can the CALs pick up underground water in the void?
So yeah, I partially answered there. So I have spoken to individuals who have used the CALs in completely flooded voids, and no, like any laser, it won't be able to measure through water. So if the void is completely full of water, then no. But with the CALs HD, if the void is small enough, I mean, Ant, you can correct me here, but I think if the void is small enough, you'll clearly be able to see if there's water in the void using the HD camera and the bright lights. But also, if you run a scan on a void that's half full of water, you'll clearly see where the water level starts, because it'll just be a noise after solid rock face.
Yeah, that's correct. Yeah, the water. Yeah, water's always a problem for laser. I mean,
Yeah.
if there's like particles lying on the water, you might be lucky and get something back. But as Mike says, you can usually tell just by the effects of the laser, of the way the laser's reflected off. The probe is IP67, so if you accidentally dunk it in water, it's not going to scan or produce data underwater, but it will survive, but not recommended.
And then the second question, it says, does this cover pipelines? I guess, does it, I mean, I guess the question is, can you inspect pipelines? And there's a follow-up question to that. If you can, does it assess the condition of the pipelines?
So, I mean, I guess we'll need a little bit more clarity on here, Sibonise, but so I'm guess if it's one big pipeline and you're feeding it in, it'll just scrape along the bottom of the pipeline. I guess it is. I guess it's a challenging one. Depends how you enter the pipeline. I assume if it's a pipeline running this way and you have a manhole that you're able to get the CALs in, I assume you'd be able to at least use the camera to inspect the pipeline. Scanning wise, it really depends on the access you have, and I think if I'm talking sense here, Anthony, like you don't want to be drilling holes into pipelines, I'm sure. So
yeah, like you said, some people have gone down into via a manhole to scan or to inspect with a camera. Sometimes if you're investigate a pipe, you want with a laser, you want very, very high precision to see if there's any cracks or anything. You might see that with the camera. You're not going to see that with this accuracy of laser. So it's not something it's usually used for unless there's absolutely no other way of getting any information. Then you can deploy this.
Okay, so that was my answer to Ola, and then
yeah, then there's another question that came from now from Yanni. What about heat?
What about heat? So so for heat, I don't exactly know what heat level rates for, Ant will be able to answer us here, but I do know the guys that survey that are updating, a few guys that are updating old survey records in some of the coal mines in Mpumalanga. And as we know, with coal mines, once they bored and pillar mines, once they've mined out the area, they seal it up to stop oxygen going into the area. So if you open up from the top a big hole, that just the whole thing spontaneously combusts. So they are doing boreholes into the underground workings to scan, to calculate exactly where the pillars are, because a lot of the times the old survey data is a bit inaccurate. So they're trying to mine down from the surface into the pillars to get more ore out of the area that has been mined out already. So in my understanding, a lot of these coal mines are constantly in a state of semi-burning underground, and their one seems to survive. But and what sort of heat would you think this?
Yeah, I think it's rated to plus 60 degrees, I think. I have put it down. Sometimes you're on a mine and they just have to get information because there's no other way of getting it. So they kind of risk the product, putting it down extreme situations. So I have been places where they've said, look, we just give it a go. So I haven't never seen one melt, or but it's plus 60 is the temperature it's rated to. Yeah.
I think perhaps maybe your biggest risk is the cable melting and then shorting out, and not the unit itself.
Yeah. That, I mean, it's rated to whatever the lowest component is. So yeah, something at 60 is rated to some. There is a component somewhere that will be rated to 60, or maybe the cable. Yeah.
Okay, Tumi said they've done a scan about approximately 50 degrees Celsius. There was another question from Checo saying, how's the azimuth drift on the gyro? Is it the same as on the bore track 2?
Yes, it's similar, yeah. So with the bore track, you tend to align it, and then you might do a number of holes. With the CALs, you tend to always align it because it's kind of a bigger deal getting the CALs deployed. You tend to align it at the start of any deployment, and then generally if it's fixed in place, you only need that gyro until it starts scanning. If it's dangling, so we have improved it so that if it's dangling and spinning while it's scanning, we can still keep up with the change in heading while it's scanning. So originally the gyros we used to produce, you had to fix it in place and then it shouldn't move, but now it can move while it's scanning. But yeah, I mean, the technology is slightly different from the bore track, but it's roughly similar, yeah, and the principles are definitely the same in terms of it. Not a north-seeking gyro, so you do have to align it. And then, like with any gyro, over time, you have to be aware that the error will be increasing over time. And it depends, and of course, it can be affected by a number of things. So if there's sudden changes in temperatures, gyros don't really like that. And really, the more it gets like swung around and knocked, the error can increase. Also, any gyro has a maximum rotation that it can monitor. So the CALs, I think it's 400 degrees per second. So if you hold the CALs, if you align the gyro and then hold it and then rotate it really quickly, it will lose track of where it is and it will throw up an error message saying that the gyro rotation rate has been exceeded. So once it's aligned, you just try and handle it fairly carefully and deploy it with care.
Thank you, Ant.
Thanks, and there's another question. Do you perhaps have a scanner that can pick up the underground voids from the surface? So that's now before you actually deploy the CALs. So, I mean,
we don't know. So if you wanted to detect something from the surface without actually going into it, you need something like ground penetrating radar or seismic measurements, gravity measurements. Yeah, there's all sorts of ways people. I mean, none of this will give you a really accurate model like you'll get from a scan, but it'll tell you kind of like, well, in Mike's presentation at the start there, you can kind of get an idea of where voids are using those methods. But they're all kind of open to interpretation, and so this gives you an actual, real hard set of data. But you have to know roughly where to go first.
And then there's another question from Christian. What is the advantage of this over the laser scanner? So I'm not sure which laser scanner you're referring to, if it's maybe the void scanner or the Quarryman or even other types of laser scanners, but Yeah.
Well,
and maybe you can take that.
If you can actually walk in somewhere, it's safe and accessible, then you won't need this. You'll just set up a tripod with a other laser scanner, which will be much more precise and faster. If you've got a big open, big stope with a big opening that you can just put a scanner out and a boom, then that's where you'd use the void scanner or equivalent. But this is for when you have no other access to a void other than down a borehole. So it's 50 millimeters diameter. So as long as your borehole's a bit wider than that, then you can deploy this down, and you can go a couple of 100 meters down the hole into the void if there's no other way of accessing it.
Yep. Thanks. And is there any other further questions for Ant or Mike? Does it look like it? Maybe I've got one question, Mike, and then we can finish.
Yeah.
What type of processing do you have to do afterwards to get your data, or is it all in real time and it's ready available after the scan? Or
Sorry,
you can say no. Okay, so generally the scans will, if you've scanned correctly, say for example you have three boreholes into one void, you scan correctly, you can just export that point cloud as it is, and then you can pull it into any third-party point cloud software to do further analysis. Obviously, Anne showed us there that if you scan correctly and you can actually get a live volume of the void as well. So there's not much that needs to be done post-processing. If you want to have anything to add there, Ant.
Yeah, no, you're just what you saw there, the model building up, you can just export that directly into any mine planning package, Vulkan, Serpac, MineSite, whatever you guys use. That will just go directly in via a DXF file or OBJ or something like that.
we definitely prescribe Trimble Business Center or Trimble Real.
Oh yeah, of course.
And then lastly, there's one more question. Can you pick up geological structures with the CAL-S?
Yeah, I mean, it depends what you mean by, like actual formations you can pick up if you do a dense enough scan. You don't necessarily see like strata, but you could perhaps pick that up with the camera depending on how big your void is. Yeah, so I mean, originally what we wanted is the size and the shape and the volume of the void. That's what we're going for. So the denser you do it, the more detail you'll have in that visual image. And then, yeah, the addition of the HD camera allows you to visual inspection as well as getting that spatial data. But it doesn't specifically tell you about what rock is or anything.
That's a good point, and so yeah, that my mind immediately when you guys released the new HD was more geological stuff. So obviously, as you say, if the void is small enough, having color imagery on the inside of voids is always a big deal, especially that you can record video footage and then save that video and export it.
Yeah. Not as much color down there, but yeah, certainly much clearer than the previous camera. Yeah.
Thanks, guys. I think that seems to be it. So thank you, everybody. We've come to the end of our webinar today. I want to thank you for joining us. Thanks, Anthony, for joining all the way from the UK. Thanks, Mike, for your contribution as well. And then I would like you guys to invite you guys to all follow us on social media, LinkedIn, Facebook, Instagram, YouTube, and also have a look at our website, www.optron.com. Thank you very much.